Too bad. First review is the one that's about arithmetic, with polynomials, it's about expansion patterns, things like that. So it's some memorization stuff. But it's nothing that's conceptually all that horribly demanding. Now the factoring stuff, I get it. That's pretty hard. I mean, there's a lot of steps, and there's a lot to see. This one, though, ought to be a confidence booster maybe a little bit. So how are we going to do this? Find the product. Okay, we could FOIL it out, right? That's always an option. But it's not the best option. And I'll tell you why it's not the best option, because what happens when you start doing things like 5x minus 4 cubed, or 5x minus 4 to the 7th, or something like that? What do we want to do instead?
Oh, I was just going to ask, could we use Pascal's pyramid thing?
Pascal's triangle? Yes, you can. Pascal's triangle indirectly is what is used for this, but better than that, I would really like you to know the expansion patterns for squares and cubes. Just memorize those, because you use them so much.
Isn't it the A minus B, or is that for the plus?
Okay, well, it's this, right? This is what we call, this is a binomial, isn't it? It's got two terms in this polynomial, and it's being taken to a power. So this is what we call, this falls under the heading of a binomial expansion. We want to expand this out into a polynomial, right? Now, I want you to know these two patterns, and you can kind of decide this for yourselves. You can decide whether you want to memorize two things or one thing for each pattern. Personally, I say one thing is better.
Yeah.
I think all you need to know is this. You fill in the blanks. A plus B squared equals what?
A squared. Minus 2.
No. Plus plus B squared. Yeah, I know what you were thinking about, Clancy. You were thinking about the A minus B pattern. And you can do that, but I would just advise against it. You don't need to. If you, and really, I mean, I know this sounds kind of, you do have, I wouldn't clutter up your storage space up here with excessive memorization. What you want to do instead, as much as you can, you want to try to, not memorize. You want to try to always, if you can think of a way to derive something very quickly without having to memorize it, that is a much more powerful way to install something in your brain. It's a lot easier. Like, for example, the distance formula. Just as a quick example, you don't memorize the distance formula. It's just Pythagorean theorem, right? It's just a manifestation of the Pythagorean theorem, so you get more mileage out of that one concept, right? Same thing with this. Now with this, rather than plugging in that other pattern for minus b, what would we do in this case? If I have 5x minus 4 squared and I want to use the pattern, the sum pattern, is all I need. What's my a going to translate to? What's my b going to translate to? Negative 4. And the fact that the b is a negative number is going to give us all the right signs when we simplify the result, right? So let's look at this one. So we end up with what? We're going to get a squared would be a cubed. Right, and that's what we're going to get 25x squared. But here we're going to get 2 times a times negative 4. Oops. Times, I don't want to do that. Darn it. I just wanted to do that. There's the negative sign, right?
Plus 16.
Plus, negative 4 squared. But a negative number to an even power is positive, right? So when we simplify this, we just get our 25, because we have to distribute the exponent to the both parts of the both factors, right? 25x squared. What's this going to end up being? Good.
Plus 16.
Okay, makes sense?
Yeah.
And so there's where your negative sign comes in. You don't need that other pattern.
And we can simplify it.
That is simplified. Now we can't do anything else to it because there aren't any
That's
like
right.
terms.
Why'd you write, is that just a new problem down below?
Yep. Yeah, but I was just saying, why don't we, why don't we want to just FOIL this out? Because really, I mean, for something like this, you probably could get away with it. It's not, if it's just a second degree, you could also FOIL it out. But when you start getting down to stuff like this, you don't want it. Then expanding it, FOILing, so to speak, you'd have to FOIL, simplify, and then distribute all the way through that product, right? That's too many steps. So we're just going to use the pattern. So what is our pattern for, let me move this down a little bit.
Don't you have to memorize that pattern, don't you?
Yes, yeah, you do. Yeah, I want you to know the one for squares and cubes.
So what if it was the 7? You couldn't
No,
memorize
then you wouldn't. Then you just use Pascal's triangle. But I'm not going to give you any of those to do, right? I mean, eventually you're going to learn something called the binomial theorem, which just tells you how you can produce for arbitrarily big expansions. There's a formula for each of the terms. But really, even that, honestly, Pascal's triangle is really good.
Can
I mean,
you show
it's-
us how to do that, please, cause it's so easy.
Pascal's triangle?
Yeah.
Oh, were you not here the day I did that?
When did you
I don't
do
know.
Pascal's
I don't
Okay,
triangle?
I'll show you again. I'll show you again. Yeah, it's a good thing to know.
Pastels?
Pascal.
I don't
Here's Pascal's triangle. This is really valuable. It's worth knowing. I might have gone through it kind of quickly when I went through it, so we'll do it again. Pascal's triangle is just this. You build the triangle. It's a geometric
Oh, I remember it.
triangle, and you always have ones. The outside coefficients are always ones, right? Each row in this corresponds to a power in a binomial expansion, okay? And we'll make that correlation here in just a second. So you always, now once I get down to the third row, now I've got to add some other numbers in the middle, right? And the rule is you take the sum of the two top numbers to get the one bottom number. So this number right here is going to be the sum of the two numbers that are above it, which would be 1 and 1, right? So that's going to be a 2. When I go down to the next row, that's going to be a 2 and 1 is 3, 2 and 1 is 3. See how we're getting this?
That sounds more confusing.
This does?
Yeah.
Did you see how we're making this pattern though?
Yeah.
These guys, it just goes like that.
So, and if those were a different number, it would.
But they'll never be. Pascal's triangle is always the same, right?
But what if so wait,
So what's on this row?
4, 6, 4, 1.
Oh, okay.
See how it works?
so wait, if the outside is always 1? Or can't
Yes,
be.
outsides are always 1 on Pascal's triangle.
So how does this help us?
I'll show you. Okay, so we'll just go to there, right?
Yeah.
Okay, so what's the point of this then? So these are all the rows for the various binomial expansions. So this first one, these are the coefficients. These are the coefficients of a plus b to the 0, so that's the 0th row. This is the n equals 1 row. And that makes sense. Doesn't it a plus b to the 1 would just be 1a plus 1b, right? Those we don't really need. N equals 2. N equals 3.
What's n?
That's the power of the binomial expansion. So let me do this. It's a plus b to the n. And these are the values of n, right? This first one was n equals 0. This is n equals 4.
Is that what we mean when they say like to the nth degree?
Yes. Yeah, an nth degree polynomial just means you're leaving it wide open. N could be 5 for a 5th degree, or it could be 2 for a 2nd degree. Okay? So let's take this 5th row. Let's just focus in on the 5th row. So what if that means we're doing a plus b to the 5th. Why is this helpful? Okay, I'll show you. Okay, so what's this saying? So this is telling us then that the coefficients are going to be, if I do a plus b to the 5th, I'm going to get 1 times something plus 5 times something plus 10 times something plus 10 times something, running out of room, plus 5 times something plus 1 times something.
What's that something?
Okay, the something. How do we fill in the somethings?
A's and B's.
They're A's and B's. Right, and here's how you do it. You know that if n equals 5, the exponents always have to add up to n. But all we're gonna do is we're just gonna stagger this. We're gonna go in integer exponents for both the A and the B. We're gonna start with all the weight shifted to the A, and then the A is gonna get smaller, the exponent's gonna get smaller by 1 each time, and B goes up by 1. So they always add up to 5, like so, right, for each term, okay? I wanna get all like iPad, or let's get all distractions away, please. So this first one then is gonna look like A to the 5, B to the 0. So we didn't even write it, right? Because 5 plus 0 equals 5. Second one is gonna be A to the 4th, B to the 1. Next one is A cubed, B squared, A squared, B cubed, A, B to the 4th, and finally, yeah. See how it works?
Easy.
Yeah, it is.
And if you don't wanna do that, you can
Oh,
just
is that
memorize the pattern.
Well, okay,
Yeah.
now, so
Oh.
you don't wanna do this for n equals 2 and n equals 3, because you use them so much, just memorize them. But you're probably not gonna wanna memorize what it is for n equals 11, right? If you ever needed to expand out a plus b to the 11th, it'd be a lot quicker for you to just whip out a quick Pascal's triangle and go down to the 11th row, right, where you get n equals 11 to get the numbers, and do that.
Have into the 11s on our tests?
No,
Oh, good.
no.
If they are, put them in as all real numbers. That way you can
But
use
I
it.
won't. I'll tell you right now, I'm not gonna do that. I'm only gonna make you, I only want you to know how to expand stuff at this point up to n equals 3. I mean, eventually you'll do more. Next year you'll do more. You know, but probably not this year. We probably just won't. It's not important. You know how to do it. Okay, I want you to notice that mouse here. I want you to notice that this is, and this is, if this doesn't make crystal clear sense, don't worry, but this is really a cool thing in math. Would you agree that A and B are arbitrary? It doesn't, I mean, I could say A plus B equals B plus A, doesn't it? Right? We know that addition is commutative and associative. I can transpose terms and it makes no difference to the sum, right? Now this is really a cool thought. This is kind of a higher level math thought. Think about this. So if A and B are arbitrary, I could interchange those values and it should not change. Like let's say that this was x and that was 2, for example. I could make it 2 plus x and I ought to get the same answer, right?
Yeah.
So then the formula that we get back for this, our expansion, has to be symmetrical with respect to A and B. Does that make sense? In other words, interchanging the values of A and B can't affect the result. It can't, because I'm allowed to do that mathematically, right? Do you see that that's the case? Look, the coefficients are all symmetrical. If I go to this page, I can like draw a line down the middle and notice that there's a symmetry to the coefficients. See, so the math gods have taken care of that for us, right? It doesn't, you get that? Yeah, it's all ties together, okay? All right, not that that's a big deal, it's just kind of a cool concept. Okay, so that's Pascal's triangle. Questions on that? That's how you do it, okay? But you don't really need to do that for stuff like this. For this, I just want you to know the squared expansion, and I want you to know a plus b cubed. Okay, what is that one?
A
Plus.
plus 3
Good.
A squared B plus 3AB squared plus B cubed.
Good. So the next coefficient is a 3. Now, if we go back real quick to the Pascal's triangle, do you notice anything? I want you to look at this row. This is kind of another cool pattern. Math is just so pattern oriented, isn't it? If we look at this diagonal right there, those represent the first coefficients in the expansion, don't they? Do you see a correlation between those and anything up there? Could, for example, if I wanted to go down to like n equals 21, could you tell me what the first coefficient would be?
21.
It'd be 21, wouldn't it?
Oh, yeah.
See how that works? Okay, after that it gets a little more mysterious. But that helps, doesn't it? That helps you with this first pattern, for example. Because you know that's got to be a 3 if you just, right? Because it's a cube. Okay? And really that's all you need, isn't it? If you think about it, that's, you know, if you're going to play math detective here, you know there are going to be 4 terms, don't you? Right? If I expand this thing out, I'm going to get terms for the cubed, the power of 2, the power of 3, 2, 1, and 0 for the constant. I know I'm going to get 4 terms. if I know the coefficients of the first two are 1 and 3, it has to be symmetrical, so the last two have to be 3 and 1. Right?
And that's all that's gonna be on the first review?
Yeah.
So it shouldn't be very hard.
No, you'll see it's not. It's not. So, okay, so let's do this one, yeah. So what do we get? So if we expand this out, once again, what's our A? 5x. What's our B?
Negative 4.
-4. So if we just follow this expansion, you got to be careful that when you write, if A is 5x, if it's a product of two factors like that, a 5 and an x, you got to make sure that you're inclusive, right? That's one thing though. And in math, the way we say one thing is a quantity. We got to put it in parentheses to treat it as one entity, right? So this has got to be 5x quantity cubed. You see that? Okay.
Yep.
Plus 3 times 5x quantity squared.
Times
Negative 4.
Good.
Plus 3 times 5x times negative 4 squared. Plus negative 4 cubed.
Okay, so that's going to give us what for the what's 5 cubed?
That would be 215, something like that.
125 plus 25 times 12 would be we can do 12 and 4 times 25 is 100, right? So 12 is just 3 packets of 4, so it's just 300, negative 300, right? You see why it's negative, right?
Yeah.
Okay, notice that the b took care of that. The fact that b was negative to an odd power, right? And what's my power of x? Squared. Then here we're going to get 15 times 16, which is just 16 times 16 minus 16, so it's 240. See how you can do that?
You're so good.
Well, but no, you guys should learn how to do that stuff. It's not hard.
Oh.
15 times 16 is just, that's 16 times 16 is just 16 16s, right?
Minus.
Well, isn't 15 times 16 just 15 16s? So it's 16 squared, which is 256, minus 16, so it's 240. So you can do that? Okay. What's the sign going to be?
Plus.
Positive, good. X to what power? Right? Makes sense, doesn't it? Look at the pattern. It's a polynomial. X cubed, x squared, x, and then finally,
Negative, whatever, 4 cubed.
what's 4 cubed?
Let me think.
16 times 4.
64.
Wow.
I was gonna say that.
Okay.
You got that. And Ellie.
Okay, makes sense?
Okay.
Okay, this guy. Now let's this isn't a hard problem, but let's talk about this for just a second because you want to be efficient and smart about this. You can do this many different ways, but it helps to simplify by sort of following PEMDAS a little bit. You know, the guide that PEMDAS gives us it's useful. Think about what it means now. If I take something to a power, that's called exponentiating. That makes things blow up in a hurry, doesn't it? Right? Numbers, I mean, and we saw that with our list of perfect cubes. You know, I mean, 9 squared is only 81. 9 cubed is 729. That's a really big number, right? Things get big in a hurry when you take them to exponents. We even see the same thing with variables. If you multiply like bases, you add the exponents. But if you take a power to an exponent, you multiply the exponents, right? And so you end up with these large exponents. So moral of the story, do I want to distribute this thing first, or do I want to simplify inside first?
Simplify.
We want to follow PEMDAS, and we want to simplify inside first, don't we? Okay? It's going to make things we're going to deal with smaller values if we do that. Okay, so we get then, what do we get inside? Well, the 5 and the 3 are already simplified. I can't simplify that ratio, can I?
No.
So I've got a 5 on the top and a 3 on the bottom. What about, where do you see x's?
Only on the top.
Only on the top, and it's to the 0 power.
This is 1.
1, yeah. Anything to the 0 is equal to 1, isn't it? So the x, that just goes to 1,
Bye-bye.
okay? What about the y's? Well, I've got a y on the top and a y on the bottom. What's my rule for dividing powers?
Whatever you go with the positive value.
Good. Okay, we're going to keep the base where it has the most power, which is on the bottom, right? and subtract the other exponent. So on the bottom, we get y to the 3 minus negative 7, which is,
Plus 10.
right?
Yeah.
Okay, and then
Z to the 5th.
z to the 5th on the bottom. And now the last thing left to do is just distribute that too, right? Distribute it to all the factors. How many factors are there?
3.
No?
4.
4.
Why?
1, 2, 3, 4.
Oh.
Okay. So we're going to distribute it to all those places, and when we do that, we're going to get 25 on the top. Good.
9. 25 plus
Y.
25.
Y to the...
100.
12.
Okay, so these are your options. The exponent for y, is it going to be 12, 20, or 100?
12.
20.
20. How come?
Because you times it.
Good, because if you take a power to a power, you multiply the exponents, right?
I thought you added them.
Z to the
To the
10.
10. Wait, why don't you add them? I think you add them.
You add them when you multiply.
Okay, here's the difference. Here's when you add them.
Oh, yeah, I got it.
You got it? Okay. All right, so now one other little wrinkle here. What if, hypothetically speaking, what if this had been, let's say, a negative 2? That looks like, oh my gosh, that's making it so much harder. It doesn't at all. All you do is flip the fraction, right?
Yeah.
Okay.
So it would be,
25 would be on the bottom.
it would be
Yep.
all over 25.
Yep.
9y to the 20th, C 10 over 25.
And we want to write these, as rational functions, which means you just want to write them as a numerator and a denominator. If the denominator is 1, it just becomes a polynomial, right? Or become, maybe not polynomial, it just becomes, then it's not a rational expression, it's just going to be some, some product of powers, right? Okay. But rational just means it's going to be, a big top, big bottom. We're not going to bother trying to put things out in front. We're just going to make it a big fraction. Okay. So in other words, we don't want to take this, like sometimes people want to do things like take the 25 ninths out. No, don't do that. Just leave it like that.
But you can simplify it, like say it was 4 on top and 8 on the
Well,
bottom.
then you could, sure. Then you can reduce the fraction. You want to do that. But ultimately, you want to just leave this thing as one big fraction, and that might sound arbitrary, but it's not. When you get to calculus, much of the analysis you do in calculus, you're going to want to have it written as in rational form. So why not? And that's ultimately we're all moving towards calculus. So that's what we're just trying to get prepared for calculus. Yeah.
What does arbitrary mean?
Arbitrary just means kind of random, doesn't make any difference.
Can I go back?
Yep, you can. Okay, what about this? Quick one.
Oh no, it's probably a pattern.
Okay, well, it sort of is. Now, we could just FOIL these out, right? The fact that there are x's and y's in there, does that complicate things?
No.
Not really. I mean, we're just going to end up with some terms that have x squared, maybe some terms that have x times y, and some terms that have y squared, right? Now, in this particular case, though, there is a little pattern you can exploit here. What do you notice about those?
They're the same.
What do we call that relationship? Okay, right, okay, good. Those are the key vocabulary words. This is a conjugate product because 8x minus 3y and 8x plus 3y are conjugates. Everybody get that?
Yeah.
Okay. Same two terms, just but in one case they're being added, in one case they're being subtracted, right? And then that ends up giving us always a difference of squares. So whenever you multiply conjugates, you know you're going to get the first term squared. So 8x squared minus 3y quantity squared. So 64x squared minus 9y squared, right?
Wait, so you have to write that all out?
You'd have to expand that so that your final answer would be 64x squared minus 9y squared.
You don't
That's
need
it.
to times the A.
Well, you can, but they're just going to cancel. Because look, I'm going to get, with a conjugate, they always cancel. I'm going to get plus 24xy minus 24xy. They'll go away.
That's on the test.
Say it again.
That's on the test.
Might be.
Wait, that was simple just to skip the second step.
When is this time?
I'll probably start it on Friday.
This Friday?
Yeah.
Whoa. Just part 1, right? Or?
Well, I'll put them all up. Yeah,
Oh.
I've only got 2 reviews. I thought that was enough for the moment.
That is enough.
This review, now really, keep this in perspective. This review This is not, you guys are not gonna have a hard time with this review. Really, you're not. This is just a matter of, you gotta remember a few patterns, you gotta, it's a lot of kind of tedious work. You gotta multiply polynomials, but that takes a little practice. Part of math is being exacting and knowing, getting to a point where you can write things down on a piece of paper well enough as you're doing your work that you don't make those simple mistakes. None of this is hard, but there's, it's easy to make small mistakes. Yes?
Okay, so yesterday my dad said that there's only 37 days of school left.
Mhm.
So are we doing like another small chapter to close in?
Yeah, we are. Yep. We're doing a little more stuff. We're right about where we need to be.
Will we have a final? Okay.
I would go.
We'll talk about that later.
I cannot remember. I can't remember this 2 weeks later.
Right. Okay, so what about this guy? Quick, we got stuff to cover. So what do we do here?
Would it be better to times them all together and then add what they're being to the power by?
Okay. What do you mean by that?
Like times what's in the parentheses together first and then do the
Well,
powers
if you
together.
could, you would, but there's nothing in there to multiply together, is there?
Oh,
Right?
no.
We have no like bases. Good, so we'll distribute the exponents, right? Because really what we have here, we have a product to a power times a product to a power, right? So we'll just distribute the exponents. If I distribute the 2 all the way through, what am I gonna get from this first factor? W to the 12th, good. Times
64.
negative 64.
Why negative?
Because if I take a negative number to an odd power, it's always negative, right?
Oh, right.
And why is that W to the 9?
I just so we don't get the negative sign confused,
Oh, okay.
that's all.
So they
Okay,
could all.
and so we end up with 640 minus 64, 576, and negative, right?
Uh-huh.
So now that you 9 times 64.
Okay, what's the power of W?
12.
9 plus 12.
So 21. Multiply like bases, we add the exponents. X to the 4th, right?
Yes, that's right.
That's it. Okay?
Makes it look so easy.
It's not hard.
Like in your head.
Well, you just doing math, you get better at that. It's not. Okay, what about this one?
Let's put it all on the top.
Okay, this is probably a good one to go through.
You scratch them off like the.
Okay, so can we use, now we're doing polynomial division, right? So can we use synthetic division on this?
No.
I bet
We cannot,
Just kidding.
which is unfortunate, because synthetic division is very, very helpful. But why is it that we can't use synthetic division here? Okay, what about the bottom, right here? It's not linear, right? The bottom, to do synthetic division, the bottom I have to be able to write the bottom in the form x minus k, right? Where k is just some number, right? That's much more complicated, right? So, yes?
And how do you do when there's like multiple things on the bottom and then you just synthetic divide this by 2?
Okay, so, yeah, in some cases, right, in some cases you can. If you know you've got factors on the bottom, you can synthetically divide 1 through, get an answer, divide that through synthetically, right? So you could nest the synthetic division if you do that. Yes, sir?
Can you cross out like terms like
No.
just the X?
No, you can't. You can't do that. Let me defend why, because that's a real common question. And this goes back to like Algebra 1 stuff. You can only cancel vertically common factors, things that are being multiplied by the whole top and by the whole bottom. I'll give you an example. Like, what if you tried to do something like this? What if I had, say, 2 plus 8 over 2 plus 3? If I could cancel out common factors or common terms vertically, people might say, oh, the 2's, right? So if I cancel those out, what do you mean by cancel them out? Where they go away or they just...
Disappear for now.
Okay, so say they went away. You'd get an answer of 8/3. That's wrong. Say they just became 1 over 1. Right? Say you just reduced them. Still wrong. in that case, you'd get 9/4, which is also wrong. What should the answer be?
11/5.
Well, 10/5, which is 2.
2.
So do you see my point? You cannot do that. You can only cancel stuff that's being multiplied by the top and the bottom. Now, I'll give you a different example. What if you had something like 4 plus 16 over 4 plus 6? Okay, now I could factor out a 2 from the top, couldn't I? Right, and I could write the top as 2 times the quantity 2 plus 8, right? On the bottom, I would get 2 times the quantity 2 plus 3. I can cancel those because they're being multiplied by stuff on the top only, right? It's a factor of the top. So there, I could cancel those and reduce this. Okay, real quick. Okay, how many factors are there?
6.
No.
5.
I could say 3 would be a legitimate
Oh,
answer.
just
You might even say 3 is right, but you could also say maybe 4. But 3's fine. Why 4? Oh, yeah, actually, okay, yeah, that factors, doesn't it? I didn't mean to do that. Let's make this. Now how many? 3. And maybe you could say x is 2, because it's x times x. But think of it as 1, that's fine. There are 3 factors there, right? How come?
there's 3 parentheses.
Because there are 3 things that are being multiplied together in that expression. You understand that? That's what a factor means. Factors are things that are being multiplied. Okay, how many terms are there in the middle factor? 3. Okay, because terms are the things that are being added or subtracted, right? Does that make sense? Okay, now think hard about this one. What if I do that? How many factors are there in that expression now?
3.
0.
1.
Whoa.
0.
I thought you were stricken it, but then you really stricken
Yeah. Now, why
Because
0?
they're not
Let me
multiplied.
tell you, yeah, exactly. Because for something to be a factor of that expression, it has to be only multiplied by other stuff, right? That's it, okay?
So if it was divided by
So when I
3.
add 3 to that, there is nothing that's being exclusively multiplied there. The 3 is being added to this stuff. So there are no factors there in that expression. Now, there are factors of that part of the expression is broken into 3 factors, but as a whole, I, for example, if I had something like this, if I had that on the top and I had like 2 plus x on the bottom, can I cancel those? No, I can't. I can't cancel those because there's a plus sign there.
But if there wasn't, you could.
If that were gone, I could
What if
cancel.
2 plus x and then add 1?
I still couldn't do it because 2 plus x plus 1 is not a factor of the top. You get that? Okay. I mean, that stuff we probably need to spend more time on earlier. But I mean, that's really important that you get that. That you understand what a factor is. Okay. What if I do this?
Then yes, because they're multiplying.
Okay, how many factors are there in the numerator?
2.
The answer is 2. Yeah. Do you see that?
Yeah.
Because I've got this big blob of stuff being multiplied by this little guy, but there's 2 things being multiplied there. Okay? So there's 2 factors. Okay? You can only cancel common factors. All right, so long division. Long division, once again, is not hard. It's just tedious, and you got to be very precise and careful, or you're going to make mistakes. So how do we set this up with long division? What goes where?
3x cubed
Okay, so this bottom goes outside, right?
outside of the bar. The little, what would you call that? The radical.
I just call it the denominator. I can't remember what the other terms are. And then the numerator goes in here. Now, what do I have to be careful about when I write the numerator out?
So added any missing exponents.
Good, I have to preserve, now I want you to think why. Don't just remember that you do that. It makes sense if you think about this. I have to preserve a column for every power of x, because even if a column is missing, or even if a term is missing in the first, in the denominator itself, maybe it's even missing when I distribute, but eventually I'm going to keep subtracting many times in a row vertically, aren't I? Eventually, I may end up with a term that needs to be in that column. You see that? So I gotta account for that possibility. I have to preserve all the powers of x from x to the fourth down to my constant. In this case, it's not a problem because they're all present in the original denominator anyway, right? Okay, so we get 3x to the fourth plus 16x cubed plus 9x squared minus 12x minus 23. So what do we do when we're dividing polynomials? What's the first step? Good. Okay, good. We're going to divide the first term in the numerator by the first term in the denominator. And that tells us what the first term of the polynomial part of the answer is going to be. So this is what we're doing. We're focusing on this quotient right there, right? Another way of thinking about that is you could ask yourself the question, when I distribute, 3x cubed times what is 3x to the fourth? It means the same thing.
X.
X.
Oh,
X, right?
not X squared.
So I get an x for my first term. What do I do when I get a term on the top, a term in my polynomial part of my answer? I distribute it through. Good. So I'm going to distribute the x all the way through. Now what does it do? Think smart about this. If I multiply a polynomial by x, that's easy. What's it doing?
Bringing the power.
Yeah, it's just bringing all the exponents up by 1, but the coefficients stay the same, right? So I'm just going to get 3x to the fourth plus 1x cubed minus x squared minus 5x. What do I write next?
Parentheses minus.
Good. Okay, we're going to subtract the whole quantity, right?
Yep.
Okay, first ones have to cancel, and they do. 16x cubed minus x cubed, 9x squared minus negative x squared, good, plus 10x squared, 12x minus negative 5x.
Okay, why don't we do 5x?
And then a minus.
Why would it be what? Where? Right there? Because I'm distributing this x through. X times negative 5 is negative 5x.
Oh, over there.
Yeah.
I got it.
Okay? And then I bring down any remaining terms to that row, because I'm really just subtracting 0 from them. And I do it again, start over. Okay, so now I get 15x cubed divided by 3x cubed is what?
5x. No, just 5.
Okay, now I got a constant, right? And I know that what I'm getting up here now, remember, these are the terms in the polynomial part of my answer. So when I get down to 5, that's the last hurrah for that polynomial, isn't it? That's the last term in the polynomial.
So there's only 2?
So I know that I'm only going to have to distribute one more time, and then I may or may not get a remainder. But it's going to happen on this step, isn't it?
Uh-huh.
Okay? So if I distribute that through, what do I get?
Minus 5.
And then minus 5.
Okay, I'm going to subtract the whole quantity. Cancel.
5x squared.
Okay, and that's my remainder, isn't it?
Yeah.
Because now 3x cubed will no longer divide into this, right? X squared, 5x squared. So that's my remainder. And so my answer is just going to be this plus my remainder divided by,
The one outside. The
yeah,
denominator.
exactly, the denominator. So my final answer then would just look like we've got this nicely color-coded. It's going to equal x plus 5 plus my remainder, oops,
Over the other.
Over the
Yeah.
divided by my original denominator.
So, but you don't have to simplify that, right?
No, you in fact, well, no you don't.
And if you had no remainder, it'd just be the
Yes,
Okay, but when's that
Yeah.
parking match?
what's that?
When's that parking imaginary, if that was the five plus X, that one would equal with that parking match?
Say that one more time, I didn't catch that.
Okay, if five, X plus five went into it evenly, then the X plus five, that has to be imaginary.
No, then that just means, all that would mean is that the remainder is 0. And so, I'll give you a quick example. What if you had, we can do one that's really simple. What if we had something like x squared minus 1 over x plus 1? If I divided that out, what I'm gonna get is x minus 1 plus 0 over x plus 1.
But we still need the 0.
No, you don't. You wouldn't write it. No, that's not there. So it's because this is a factor of x squared minus 1. In other words, x plus 1 times x minus 1 is exactly equal to that.
So
Okay.
that makes it like these imaginary.
Okay. Okay, we're on to, that's the whole first review, done, out of the way. Okay, now we're looking at the second review. Now, this is the one, I think this is, out of all of them, what I'll probably do, honestly, and you guys, now, really, this is good. You're glad I'm doing this. I'm gonna turn this section into probably like 4 really small tests.
Like
So
two
each,
problems.
well, I mean, like, you know,
What's your
Like
really
small.
Yeah, cause you say short and then they're like 12.
no, this will be like, I'm
Like
thinking,
6 questions.
yeah, 6 to 8, something like that. Yeah.
Although then if you miss one, you pretty much fail.
Yeah,
But you
exactly.
can take it again.
That's the
Okay,
problem.
so this is gonna be the hard one. This is the one, the factoring one's the hard one. So let's look at these. Let's look at these factoring problems. Now, what we wanna do with these, I've got to really organize our thinking on this and we can make them a lot easier. This has got 4 terms, that tells us a lot. We factor by grouping. That tells us the technique we use, right? I'm not given any other hints, I just have to factor this thing from scratch. Keep in mind, now, it's gonna work on this test because we're practicing this, but in the real world, it may or may not factor by grouping. Just because it's got 4 terms doesn't mean it will work. That's the only way we can do it at this
Then
point.
you give up.
Right.
If it doesn't work.
But I made problems that work, so they're gonna work. So this time you know you're practicing that process, so I made the ones that use that process. So when we group, we're just gonna group the even number of terms into 2 evenly, 2 subgroups with even number of terms. So each of them has 2, right? Here's group number 1, there's group number 2. This is not a hard process. You guys know this process well. You've done this clear back to chapter 5. So what do we do to the first group?
See if you can take X out.
Yes, what's the greatest common
X
factor?
squared.
X cubed.
X cubed, good. Is that us?
Yep.
Okay, we'll pick this up next time.
Are we gonna be here tomorrow?
I think we better finish this and then we'll,
Okay.
yeah.